Today we're going to look at an example of a type of identity which Ramanujan was really famous for. And these types of identities were very important for the study of integer partitions, or sometimes called additive number theory, which was one of Ramanujan's main topics of study. Okay, so let's look exactly at what we'll prove today. So it's a bit gnarly, but we'll talk about why it's kind of like not as pretty as you might think it would be. So the left-hand side looks like this. So it's this infinite sum of terms which themselves kind of build as bigger products. So here we've got 1 over 1 plus x times 1 minus x over 1 plus x times 1 plus x cubed plus x squared, 1 minus x squared, 1 plus x cubed, 1 plus x to the fifth, and then that continues on and on and on. And I think you can probably see the pattern from these first three terms. And what we'll show is that's equal to the sum as n goes from 0 to infinity of minus 1 to the n, x to the 2n times n plus 1. And you can either think of this as a formal power series, or this is happening inside of the region where the absolute value of x is less than 1. Okay, so before we get started, I'd like to point out that you probably know something about geometric series from a first or second semester calculus class. And those are generally of the form, the sum as n goes from 0 to infinity, a sub n, where that's some number, and then x to some linear polynomial in the variable n. But something called a hypergeometric series has the same form, except in the exponent of x, we have a quadratic polynomial. So that makes the difference here. And you might say, well, what about a cubic or a quartic or so on and so forth? I think that's probably also considered a hypergeometric series, but I'm not sure if those have been studied really at all or as much as these cases right here. Okay, so let's get into it. And we'll start by defining a couple of generalizations of the left-hand side of our proposed identity. So we'll call L1, well, exactly this left-hand side. And then L2 will be, well, pretty similar. Notice that it differs by the fact that we have an x cubed down here, so it's 1 over 1 plus x cubed. And then we have an x cubed times a 1 minus x cubed. And then our product here starts at x cubed. So we've got 1 plus x cubed times 1 plus x to the fifth. So looking at it like that, it looks like in some places we've exchanged x for x cubed, but in other places we're just like moving the portion of the product that we have. So instead of these two terms, we've got these two terms. And then we can see this continuing on. And then we'll keep going. So in the next one, we'll have x to the fifth. So it's going to be 1 over 1 plus x to the fifth, plus x to the fifth times 1 minus x to the fifth over this product of two terms starting at 1 plus x to the fifth. And then so on and so forth. Okay, so now we're going to use these as a tool for getting at this right-hand side. And we're going to start with the following fairly simple observation, and that is that for any value of k, we can take 1 over 1 plus x to the k and rewrite it as follows. So this is going to be 1 minus x to the k over 1 plus x to the k. So you can put this right-hand side or the two terms on this right-hand side together, and you'll see that you easily achieve that left-hand side. But now what we'll do is we'll take this very simple identity and we'll use it to replace the so-called top terms in L1, or really in general in Ln. And well, what do I mean by the top terms? Well, in this case, I would consider the top term this 1 over 1 plus x. Whereas in this second summand, my top term is the 1 over 1 plus x cubed. Then in this third summand, the top term is 1 over 1 plus x to the fifth. And then you can go on and on and on. And then similarly down here, the top term of the first summand is 1 over 1 plus x cubed. The top term of the second summand will pick up this 1 over 1 plus x to the fifth, and so on and so forth. Okay, so let's see what that does to L1. We're actually going to be working mostly with L1 and L2, and well, very, very similar arguments will apply to Ln plus 1 and Ln. Okay, so let's get at it. So we're going to take this 1 over 1 plus x and write it as 1 minus x over 1 plus x. So that's our first term. And then for the second bit, we'll have x times 1 minus x over 1 plus x times 1 minus x cubed over 1 plus x cubed. So like I said, I'm going to make the replacement for this top term over here. And then I'll do the same thing for the next bit. So I'll have, let's see, it'll be x squared times 1 minus x times 1 minus x cubed. So my denominator will now be 1 plus x and 1 plus x cubed. And then my so-called top term will be expanded as 1 minus x to the fifth over 1 plus x to the fifth. Okay, good. But now what I'll do is I'll maybe like distribute all of these together and then recombine. So in other words, I'm going to split this up into all of these first terms, which of course I get from distributing through, and then all of these second terms, which of course like they're going to change from the distribution of the common factor as well. So let's see what that's going to leave us with. So we'll have a 1, and then we'll have plus x times 1 minus x over 1 plus x. That's from the second term. And then plus x squared, 1 minus x cubed over 1 plus x times 1 plus x cubed, and then plus dot, dot, dot. And then maybe I'll put some magenta parentheses around this just to show that it's coming from the magenta underline. And then from that, we need to subtract what's going on with the blue underline. So that's going to have our first term as x over 1 plus x. And then let's see, my second term will be x to the fourth because I've got x times x cubed. And then I have 1 minus x over, let's see, 1 plus x times 1 plus x cubed. And then let's write the next term down, and that'll be an x to the 7. We have a 1 minus x, a 1 minus x cubed, and then in our denominator, we'll have 1 plus x cubed, 1 plus x to the fifth. Great, and then since this is all coming from the blue underline, let's change this parentheses to a blue parentheses so we can see like how that matches to what we have above. So now what we're gonna do, let's like take this version of L1, we'll put it at the top of the board, and then we'll build a second version of L1. Okay, so this is what we already gained. And now we're going to make a similar substitution for this 1 over 1 plus x to the k term to get another version of L1. And so let's present that as another following simple observation. And that is, for all values of k, we have 1 over 1 plus x to the k can be rewritten as 1 minus x to the k over 1 plus x to the k. And then plus x to the k over 1 plus x to the k. So again, I think that's pretty clear. If you push those two together, you'll see that it simplifies. And then again, we're going to replace what I called the top terms. Maybe the top terms in each summand, just like we did before. Okay, so that's going to give us a new version of L1. So let's see, my top term in this first summand is 1 over 1 plus x. So I'll rewrite that as 1 minus x over 1 plus x over 1 plus x. And then for my second term, well, I'll have that common factor first. That's an x times a 1 minus x over 1 plus x. And now I'm replacing the 1 over 1 plus x cubed. So that'll give me 1 minus x cubed over 1 plus x cubed minus x cubed over 1 plus x cubed. Great. And then that's going to continue on and on and on. So let's see, my next term will be x squared, 1 minus x times 1 minus x cubed over 1 plus x cubed, and then making the top term replacement, I have 1 minus x to the fifth over 1 plus x to the fifth minus, plus, and this should have been a plus as well, x to the fifth over 1 plus x to the fifth, and then we keep going. Okay, nice. But now we're going to pull that apart into two pieces as well, based on these first terms from each set of parentheses, and then also these second terms from each set of parentheses, which I'm underlining in green and red respectively. Okay, so let's see what that leaves us with. So inside of the green parentheses, which come from the green underline, we're going to have 1 minus x over 1 plus x. That's our first term. And then plus x, 1 minus x cubed over 1 plus x cubed. And then for one more, we have, let's see what it'll be, x squared, 1 minus x cubed, 1 minus x to the fifth, all over this product 1 plus x cubed, 1 plus x to the fifth. And then that keeps going on and on and on. So that's our green parentheses coming from the green underline. Okay, so now let's see what we're going to get for the red parentheses, which will come, respectively from the red underline. So the first bit will be x over 1 plus x. And now we'll have, let's see, x to the fourth, 1 minus x over 1 plus x times 1 plus x cubed. And then, well, that's going to continue on and on and on, so I won't write the rest of the terms. So we've got something that looks like that. Okay, so now let's maybe put this second version of L1 up at the top, and I'm actually going to, for good measure, multiply it by x, as that's going to be important for our simplification. So there we have it. There's our two versions of L1. The second one I multiplied by x, as that's going to lead us towards a simplification, which is almost immediately apparent, given that this first summand in the xL1 is the same as this second summand in this L1, I guess from the first large term. And then that keeps on going. The second summand here is the same thing as the third here, and so on and so forth. So that motivates us to take a difference. So we'll take L1 minus x times L1. So I'll maybe write that as 1 minus x times L1. Okay, so let's see what that's going to leave us with. Let's cross out what cancels. So like I said, this term is going to cancel with this term. I'm canceling them both in red. And then this term cancels with this term. I'll cancel them both in blue, and so on and so forth. And then we've got this top 1, so I'll just bring that down. So we've got a 1 and then a minus. Well, let's see, since we're taking a difference here, we'll notice I've got a common denominator, so that's going to turn into x times 1 plus x over 1 plus x, after factoring the x out. Then I can do something similar for the next bit. I can factor an x to the fourth out. So we'll have a x to the fourth, which we can factor out of these two, and then that'll leave us with a 1 plus x, then a 1 minus x, all over a 1 plus x and a 1 plus x cubed. And then for the next set of terms, I can factor an x to the 7 out. And then since we have a sum of the two, we'll be left with 1 plus x, Then we've got 1 minus x times 1 minus x cubed. And then let's see, the denominator will have a 1 plus x, a 1 plus x cubed, and a 1 plus x to the 5th. And then that's going to continue on and on and on. Okay, but I think you can probably see we're going to get some simplification. That simplification is going to take us in a good direction. So here this 1 plus x will cancel this 1 plus x, and that's going to happen in all of these. So let's get all of those taken care of. And then let's observe that we can put these two terms together into a 1 minus x. I'll maybe put it in parentheses as well. But notice that all of the rest of these have a 1 minus x in them as well. So let's maybe put some boxes around that. And then we can factor 1 over x out of everything. So that's going to give us 1 minus x, and then we'll be left with 1 from factoring out of this first term. And then minus, well, let's see, we'll have x to the 4th over 1 plus x cubed. And then minus x to the 7 times 1 minus x cubed over 1 plus x cubed times 1 plus x to the 5th, and then so on and so forth. But now, let's look at this carefully. Well, first of all, these two 1 minus x's can cancel. And then all of these trailing terms here have an x to the 4th that can be factored out. So bringing all of this down, we have L1 is equal to 1 from this, and then minus x to the 4th, which can be taken out of everything. And then this first term will be 1 over 1 plus x cubed, but that's the first term of L2. And the second term will be x cubed times 1 minus x cubed over that product. That's the second term of L2, and so on and so forth. So here we'll get L2. So we've got L1 equals 1 minus x to the 4th times L2. And then, well, like I said, we're just going to be working directly with L1 and L2, but maybe more generally, and you can check this, details are essentially the same, you just have some variables and exponents. More generally, we have Ln plus 1, or sorry, Ln is equal to 1 minus x to the 4th times Ln plus 1. And that recursion is really the last thing we need to do to quickly get at this identity. So let's do that. Okay, fixing a tiny typo on the last board, this Ln should decompose as 1 minus x to the 4n, not x to the 4, times Ln plus 1. And now we're ready to take it home. So here I've got this left-hand side of our proposed identity written up, but let's recall that that was equal to L1. But then, like we said before, we can write L1 as 1 minus x to the 4th times L2. But now we can apply this again, and we'll get 1 minus x to the 4th times 1 minus x to the, let's see, 4 times 2, which is 8, times L3. And then we can keep going on and on and on. So maybe I'll write one more down. So this is going to be 1 minus x to the 4th times 1 minus x to the 8th times 1 minus x to the 12th times L4. Again, applying that recursion to L3. Now we can kind of see where we're going. We'll have this infinite expansion. So we'll have 1 minus x to the 4th times 1 minus x to the 8th times 1 minus x to the 12 times 1 minus x to the 16 times 1 minus x to the 20, and so on and so forth. So 1, 2, 3, 4, 5, 6. So I need 6 parentheses to close it. But of course that's infinite, so I really have infinite copies of parentheses there. Okay, but now let's maybe multiply this out and see that we'll get 1 minus x to the 4th. So that x to the 4th comes from the minus x to the 4th times 1. And then it'll be plus x to the 12. So that's from x to the 4th times x to the 8. And then let's see, it'll be minus x to the 24. That'll be from the x to the 4, x to the 8, x to the 12, and then plus x to the 40, and then minus x to the 60, and so on and so forth. But if we think about this as 4 times 1, 4 times 2, 4 times 3, and so on and so forth, what we actually get here is the sum, as n goes from 0 to infinity, of minus 1 to the n, and then x to the 4 plus 8 plus added all the way up to 4 times n. But now what we can do here is factor a 4 out, and we'll get the triangular number 1 plus 2 all the way up to n. But that has a fairly well-known closed form of n times n plus 1 over 2. Multiplying by the 4 will give us this exact expression right here. So now bringing that up, we'll have this is all equal to, the sum as n goes from 0 to infinity, minus 1 to the n, and then x to the 2n times n plus 1 as needed. Okay, so there we have it. Like I said before, this is an example of an identity that is due to Ramanujan. And Ramanujan has tons of identities like this, and that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.